Hello YouTube, it's Greg, and today I want to talk about removing PFAS with GAC. It is raining behind me, so you might hear that. But anyways, so what is GAC and what is PFAS? I guess I'll start with what is PFAS, but basically PFAS is pure and polyfluorinated alkyl substances, and in this video I'm going to talk about specifically PFOA. And I'm going to talk about FPBA a little bit, but when we get there, you'll know what it is. Basically, PFOA is a carbon chain. Some of them are completely fluorinated. The last one is almost completely oxidized. It has 3 bonds to oxygen. One of these oxygens is... can I get a laser? Yes. One of the oxygens is bound to hydrogen, and then you could put this, when PFOA enters the water, or in general, like it could be like a 3 carbon chain, or maybe even 6. In general, when this almost completely oxidized carbon enters water, it loses this proton and becomes negatively charged. And that's kind of one reason why I prefer to stain the water. Because, charges vastly prefer to stain the water. As you can tell, it's not that favorable to stain the water. As the chain gets shorter, it's been observed that it's actually more favorable to stain the water. But anyways, another kind of issue with PFOA is, I go about this a lot, not into great detail in my previous video, but basically PFOA actually forms in my cell, which is basically a circle. Well, it's not really, but I'll talk about that a bit later also. Basically, PFOA, when you have multiple PFOA molecules together, and they lost a proton, they come together and form a sphere, a ball in the water. And this is where the unprotonated, almost completely oxidized carbon points outward, and basically this fatty tail points inward, and this basically makes a sphere. It's basically soap. That's why it's kind of an issue, because it just goes everywhere, right? It stays in the wastewater treatment plant, it stays in the water after it goes out. It's a bit of an issue. I want to make a whole separate video about that, but I don't want to talk about it here. And so basically, a granular activated carbon is carbon that has been heated to very high temperatures with no air. So it's not burning in the presence of air. That would just... it's different from charcoal, but pretty similar to charcoal. That's why it's called activated charcoal. Yeah. But basically, this is in your Brita filter. And so basically, it's just really cheap, easy, convenience. You could use any type of carbon source. Well, not any. There's preferred carbon sources. But basically, it's very common. It is readily widely used in our systems, right? Like once you have wastewater treatment plant, they very often, for one of the many processes, is that they very much pass it through granular activated carbon. It's cheap, it's already in the system, it's widely available, and so considering how much of a common issue PFAS is, GAC would be a great way to solve this PFAS issue, since they're both very commonplace and GAC is very inexpensive. And so, can you actually see that? That's actually kind of annoying. But whatever, you guys can see it. But basically, when let's say you get like 100,000 liters of wastewater, right, and you just bring it to the wastewater treatment plants. What happens is they basically take that water, put it in a giant tank, and they put chlorine gas and octanol, and they kind of just, they don't heat it up, but it naturally gets very hot, because it's a lot of reactions going on, and basically as it cools down, you're gonna have partitioning. Ooh, fancy word. But basically you're just gonna have separation. Right? Because you added octanol, right? Which is, mostly fat, right? Like I said, it's octanol is a carbon chain. The last one, or rather the first one, is has one bond to oxygen, and that oxygen is bonded to a hydrogen. And so basically, you're gonna have a lot of different partitioning and separations. Things are gonna want to prefer to stay in the water. Maybe they would rather stay in the octanol. Like, it's a grease, it's a fat. Doesn't want to lose its proton as fast as a PFOA, so that's why it's not so much of an issue. In addition, it's not actually a health concern. PFOA and PFAS in general have been linked to multiple different carcinogens and toxins and stuff, which I'm not. I'm a chemist, not a toxologist. So anyways, basically things are moving around, right? And so you have things that are going to partition into the octanol, like Mirex, which is a persistent organic pollutant. I'm pretty sure it was a pesticide. But yeah, it's a personal favorite because look how wonky that structure is. Wow. But anyways, you also have hexachlorobenzene, again, another not legacy, a persistent organic pollutant, and that just partitions fully into the air, right? That never stays in water or the octanol. And PFAS vastly prefers. It will make some foam. It will go a little bit into the octanol. Like I said, it's a soap. Soap combines layers, right? That's not like the true horror of PFAS in wastewater treatment plants, but that's another video I hope to make. That's kind of near and dear to my heart. But like, we'll get there when we get there. But basically, the idea with using GAC is that you're making it more favorable because like no one cares about, well, people do care about the octanol because, they do use, because that octanol is actually pretty good fertilizer. But that's a whole separate issue for another day. But so focusing purely on the water, they to get things to really move, the reason why things move is because it's more favorable to be in that place. Right? Would you rather stay in the center of a hurricane, or would you rather be in the middle of nowhere where you have no concerns of a hurricane, right? It's much more easier and to be much more appealing just to move to the middle of nowhere place than to be in the center of a hurricane. And that's kind of the same idea with chemicals, I guess. Chemicals move in terms of least energy possible. They're the most stable conformation possible, right? Like the energy doesn't change. Like it's still going to be the same thing. It's going to have the same bonds, right? But it's going to move to a place where it's not as chaotic, right? It releases a bit of energy. It's a little bit more happier. You're getting further and further away from the eye of the storm, right? You're going to be more and more happy, I guess. And so there are proposed reasons why PFOA vastly prefers to stay in the GAC, and that's going to be a small discussion later. But basically, it doesn't really want to stay in the water too much, just because it lost that proton in its charge, and it's like an ion, just like chlorine. It's still like really, really big and bulky, and it's not that happy there. Basically, would vastly prefer to be into the GAC, and so I kind of just want to. Another name for GAC is amorphous carbon, and as you can see from this picture, is that yeah, the structure is really, really wild and crazy. But this is not the true structure of GAC. And so this is a computational experiment, right? So they're finding the lowest energy, the minima of GAC under these conditions, right? But like when you're burning a carbon source in no air, right? You're gonna get different results, right? Like if you have two different chefs in the kitchen, or two separate kitchens, you ask them to make the same dish, you're gonna get vastly two different flavors, maybe even textures, maybe definitely presentation. And it's kind of like that. GAC doesn't have a real well-known structure. Like when you say this molecule is water, you know it's H, oxygen, H, right? H2O. When you say GAC, right, it's not. We just know that there's carbon and a few oxidized groups, right? Because you're burning it in the. So it's very, very wild and random structures that you don't really have good control over. And like, and I kind of hope this picture kind of just shows you just how crazy and wild the structure is, right? Like this is not accurate because this is a simulation, and like if they were to repeat it, they would get very, very similar results. Like maybe this carbon would be slightly different, or maybe this would be slightly different. Like things would be very similar, but since they're finding the lowest energy stuff, they're going to get very similar results. But anyways, the type of GAC you use matters a whole lot, right? But that again, as you can see, that's a whole other discussion for a whole other day, if ever, because it's a complex engineering topic, and I'm just a chemist, an undergraduate chemist. Um, and so I kind of just want to talk about regenerating GAC. Basically, once you have your PFAS and you've watered and you filter it through GAC, right? Now the PFAS is now in the GAC. It's no longer in the water. Great. It's safe to drink. But now you have GAC with PFAS, right? And it's like a concern. Like, what do you do with it now, right? So basically, there's this paper that I really like. It's small, concise, very much self-contained. Basically, it proposes supercritical carbon dioxide. So what's supercritical? Basically, there are multiple states of matter, right? But basically, supercritical is when there's a whole lot of pressure and temperature applied to a substance, and so it changes of form. It's to something called supercritical fluid, as most people just refer to it as supercritical. But anyways, you're basically applying a whole lot of energy, right? The ideal gas law, PV equals nRT. If you increase the pressure and keep the temperature static, you know, the pressure and temperature are directly correlated, and you're increasing both of them, right? And like, it's just gonna be, I wouldn't say a positive feedback loop, but like, because like, there's only so much energy, right? There's no such thing as a perpetual motion machine, right? But it's very, very high in energy, right? Very high energy state of matter. And so the cool thing about carbon dioxide is that it doesn't require that much energy to be supercritical compared to other things, right? And so, like, as you can see, it's basically at the boiling point of water with, yeah, okay, that's quite a bit of pressure, but it's not, absurdly high. And so basically in this experiment, they took the GAC and they took some CO2, they heated it and pressurized it, and they passed the CO2 through the GAC, and so they collected this mixture of CO2 and PFAS, and it was able to regenerate the GAC, right? And that's like super cool. And there's a lot of science going on about cleaning up GAC, spent GAC. I'm at one, as you can see from these charts, like it's super efficient, blah blah blah. One thing I kind of wish to talk about in the paper is what they did with the waste afterwards. I'm very curious what they did with it, because like once you have the things return to standard pressure and temperature, right, 24 degrees Celsius at like 1 atm, right, which I don't know what's that in bar, but basically it's going to be a still gas, right, somewhere around here. Well, I'm not going to be there, it's going to be like here or something. But anyways, the CO2 kind of just evaporates, it goes away, right? And so now you're just left with this gaseous PFAS. This paper doesn't talk about what it does with the waste, and kind of wish, they did. But anyways, and so GAC is also not the only way to remove PFAS from water, there's something called ion exchange chromatography. As a chemist, I always refer to it as ICE. But papers use so many different names for it. And I'm sure there's like some small minute difference. I never really paid attention to it, but like I saw things call it IA. um, yeah, so yeah, millions of different names for it. I'm just gonna refer to IEC or ICE in this video. But basically, ICE is much more better at removing PFAS than GAC. And the reason, obviously, is that there is a little bit more energy. It's a little bit more favorable, right? It's a lot further away from the eye of the storm, basically, right? And so this is kind of a small argument I noticed in the literature. They kind of argue about like what direct forces are responsible for it. I did put a mini a paper proving it, a discussion why I don't think this paper is applicable. It's a great paper. Oh my gosh, it is low-key one of the better written papers I've read in a long while. It's really good. I like it. Especially since it's about kind of on-water chemistry, which is something which got me into PFAS. But anyways, and so basically, I also put like a mini discussion or like proof about why this paper isn't exactly applicable. But it's not like the best argument. I also provided another paper discussing that basically just shows why the energetics of PFAS are very complicated, and why I kind of like the argument that GAC is just focusing on the fact that PFAS doesn't really like the water, and that ICE uses the fact that it doesn't like the water and the fact that it is electrostatic. I didn't talk about this, but basically, ion exchange chromatography is kind of what it sounds like. You have this resin, like this bead. Well, no, it's not. It's microscopic beads, right? Well, I'm not sure if you could see them on a microscope, but anyways, basically, it is full of. It has a surface. It's full of ions, say chlorine, and basically, since PFOA and chlorine are both negatively charged, they kind of swap places. But however, you're actually measuring the sodium content, right? But basically, it's just that you're swapping ions in place, right? That's all there is to it. But basically, there are a few differences between ICE and GAC. For one, as we already discussed, the energetics are different. There's a small argument about that, and also the chain length. Basically, with ICE, or IX as I put it here, whatever, you basically have it that the shorter chain PFAS, the PFBA in this experiment, that in most experiments use PFBA, basically PFBA makes contact with the resin first. And so as longer PFAS come along and interact with the resin, it actually just kicks out the shorter chain. So in the end, ICE does not do a good job of removing the shorter chain PFAS. However, GAC did not perform at all. Like, it doesn't remove shorter chain PFAS like whatsoever. And this kind of brings me up to a call for help, I guess. I remember I was reading a paper last fall, 2024, about how they managed to engineer a type of GAC with very small pores, and so basically these small pores allowed for the shorter PFAS to come in, and then the long PFAS couldn't enter in. So basically, the shorter chain PFAS was removed by GAC, and I can't find that paper. So if anyone knows the name or can like find it for me, that'd be great. But yeah, another thing I kind of want to talk about is green chemistry, right? So when I talked about supercritical CO2 for regeneration of GAC, it's actually like really convenient, right? You don't have to worry about any solvents. Like you don't have to worry about very high energy things, right? You don't have to worry about like wasting too much materials, right? It's just a little bit of energy, and at the end of the day, so the CO2 evaporates, and we already have tons of CO2, right? Um, and so I kind of just want to talk about a little bit about green chemistry. Again, I'll probably the only time I'll ever talk about, well, the good sides of green chemistry. Spoiler alert, there's none. Is on April 1st, but I really hate green chemistry. I really do. And I kind of just want to talk about how I think environmental chemistry, and specifically how GAC and PFAS are a good application of green chemistry. In case you don't know, green chemistry basically proposes the idea that don't work with very dangerous stuff. And consider the life cycle of chemicals in the environment. Those are like basically the two principles. However, they managed to expand it to 12. um, it's very much a very, very wordy, verbose, inconsequential idea that's put forth in chemistry. And I don't like it. Um, like I said, it's just verbose. It doesn't actually do anything. You could tell them to think about it, but what does it matter if they think about it if, it doesn't stand up uh, in the face of money, right? Like, why, like, at the end of the day, these companies are made for money. Like, these chemists, they're trade undergrad, they're going to be working for industry. They're working for money. Like, so it doesn't really teach anything about practicality, right? It's just like a joke, if you ask me. Um, However, environmental chemistry shows this like really unique side of green chemistry. Like, here in this paper, like they try using plants to absorb PFAS, and then they like destroy the PFAS in the plants, right? By destroying the plants. In comparison, like it would be much cheaper to like remove kilotons of plant matter than to move and schlep around kilotons of water, right? And to like burn water. Like water has a boiling point of 100 degrees Celsius. Meanwhile, plants are burning at much lower, right? And it's like, and so you're using lower energy, and you're using just more. It's just more cost effective, basically. And like here are papers that are talking about the economy and things like now that you have the octanol infused with PFAS, and you burn it, how can you use it now, right? You can't really use it, and so it kind of just talks about the economy and what you can actually do. And this is actually really important because wastewater treatment plants make zilch. They do not make money, right? It's really for the local people there and their jobs more than anything else. They do make some money, but like now they used to be able to sell the octanol as fertilizer, but now you have it infused with PFAS. If you put it on fertilizer on the grass, the cows are going to eat it and they're going to die. They die. You have to cull entire herds of cows because of this. And like it's loss of money for them, And so environmental chemistry implies it shows like a really massive and actual application of green chemistry that is just not thought about at all in actual green chemistry. Like, I swear, there's only one person on that board who's an actual environmental engineer or environmental chemist, and they were talked over every single point. Like, there is not a single environmental lawyer or environmental justice lawyer on that board. I swear there wasn't. Because, like, and it's just, like, so baffling to me, like, how ridiculous green chemistry is, and how it could be just so much more. I don't know, I just kind of wanted to talk about it. So that's kind of my mini rant. And so this is extra resources if you want it. Um, Again, you could just And here's my works cited again, slide numbers. Just go to the slide and whatever. Anyways, thanks for listening for me and my rants. Yeah, have a good day.